Yes,
What
and
about?
we see that. Yes.
Okay, perfect.
And
You can see my presentation.
yes.
Perfect. Okay.
Okay, yeah, it's also good like that. I guess we can all read it. Willis, would you mind introducing Anne? Oh, Willis, are you
Thank
there?
you very much, Prof. Can you hear me?
Yes, I can.
Yes. Okay. Thank you very much, Prof. Thank you, Anne, for accepting to give us this talk. And now it's my pleasure to introduce our speaker today, who is Dr. Njeri, a research associate in astrophysics at the University of Newcastle, where she has been working since 2012 with Dr. Chris Harrison's group. Dr. Njeri began her academic journey at the University of Nairobi, where she completed both her bachelor's and master's degree in astrophysics. Later joined University of Manchester for a PhD in astrophysics, followed by the postdoc. Scientific work is focused on one of the most compelling questions in modern astrophysics: how do galaxies form and evolve across cosmic time? Central to this question is the intricate relationship between star formation and accretion onto supermassive black holes. Dr. Njeri uses high sensitivity, high resolution radio observations to disentangle these processes, particularly through radio interferometry and very long baseline interferometry technique. Our work utilizes data from leading instruments such as EMALIN, European VLBI, VLA, LOFA, and LOFA, allowing her to probe the feedback effects of quasars on their host galaxies in unprecedented details. Beyond her academic contribution, Dr. Njeri is also deeply committed to education and community upliftment. She is the founder of Elimisha Msichana, Elimisha Jamii, Educate a Girl, Educate an Entire Community project that is working with girls in rural Kenya and Uganda through astronomy outreach, STEM workshops, and scholarship opportunities. A major addresses issues such as gender inequality in education, teenage pregnancy, and early marriage, striving to ensure 100% primary to secondary school transition for girls. Thank you very much, Anne, for accepting to give us a seminar today, and welcome.
Yeah, thank you very much, Willis, for that kind introduction, and also thanks for the invite. I'm happy to present my work. Yeah, I cannot see the screen, so if you have a question during my talk, you might have to speak up because I cannot see the teams, or yeah, the teams, the meeting room. I can only see my slides. So yeah, sorry about that. So just speak up. Yeah, like Willie said, my background is basically high resolution radio imaging of the extragalactic radio source population. That is a very faint radio source population at at cosmic noon. That is between ratios 1 and 2. Whereby we believe a majority of our AGN resides. But the thing is, it's very difficult to distinguish between star. Sorry, yeah, I cannot switch off Teams. Okay, sorry. I'm getting messages from my team as well, so sorry about that. So yeah, so basically what I do is I use very high angular resolution, that is the very long baseline interferometry, to try and disentangle and especially resolve this very faint AGN from star-forming galaxies, which can get very complicated at these high ratios. So I'll present some of our work from these wide field VLBI surveys and also briefly touch on the future, that is the integration of VLBI capabilities into the SKA. So if you're an AGN person, whether radio or non-radio, I'll try to convince you why your AGN observations require VLBI follow-up. I'll briefly touch on the wide field VLBI techniques and how we're increasing our VLBI sample size, and also present some of the current wide field VLBI surveys, present us some of our results from these wide field VLBI surveys, and of course, touch on the future, that is SKA plus VLBI and what that will look like. So one of the key goals in astrophysics is to study star formation and galaxy evolution across cosmic time. And multi-wavelength studies have shown that both star formation rates, so this plot here we show the star formation rates, and accretion rates tend to peak at ratios between 1 and 2, and therefore implying coevolution between these two objects, that is the host and the supermassive black holes. And therefore, in order for us to understand the physical interplay, the feedback mechanisms between these two, and also in order to obtain precise star formation rates measurements, we need to find all our AGN in these fields, because what happens is that our star formation is contaminated by accretion activity or AGN activity. So focusing on radio observation of these extragalactic radio source populations have shown unexpected upsurge in the number count source for these sources at flux densities below 1 millijanskis. You can see on this plot from Padovani, whereby we have this increase in the number source counts. And further study of these targets have shown that they are mainly composed of star-forming galaxies and AGN. So we have the star-forming galaxies, and then we have AGN, and then the AGN is further resolved into either radio loud AGN and radio quiet AGN. And what you'll notice that at these very faint flux densities, that the dominant AGN population is a radio quiet AGN, which becomes very difficult to disentangle from star formation. For radio loud, it's slightly easier to identify, but when it comes to the radio quiet AGN, you really require this very high spatial resolution. So the key advantages for using radio is that radio observations are not affected by the gas and the dust in the universe, in the intergalactic medium, and therefore our radio measurements require no dust corrections, and therefore provides us with unbiased tracer for star formation. And just to stress that these faint radio objects are highly obscured in the X-ray, infrared, and optical. So using radiomorphology, we can infer the presence of AGN in these distant galaxies, whereby, for example, in this case, we have a very bright radio object with this very powerful relativistic radio jet. So if you have, for example, observations with the VLA, so the VLA, this is a very large array. It's a radio array in the US. I'm sure some of you might have used the instrument. L-band gives us an angular resolution of about 1.5 arc second, and it's the most or widely used radio array in the world. So most of our radio data initially comes from the VLA. So if you have your VLA observations or results, you can infer the presence of an AGN on this very bright target at 22 millijanskis based on this radiomorphology. However, key to note is that this only represents a very small fraction of these extragalactic sources, but most of our sources look like this. So below 1 millijansky is very faint. At this typical angular resolutions, it's very difficult to understand what is going on in this system. And if you don't have auxiliary data, it will be very difficult to tell whether this is a star-forming galaxy or an AGN. So why VLBI? VLBI provides us with very high angular resolution and high sensitivity, and therefore enabling us to zoom into the cause of these very faint radio objects. And what do I mean? So looking at this plot, it shows the angular resolution of future, current, and past deep interferometric radio continuum surveys with some of these radio interferometry instruments. For example, for the future, we have the SKA1 MID, and then we have the MIGHTY survey by Meerkat. I'm sure some of you are familiar with the MIGHTY survey. And then we have the IMU survey by ESCAP, and then we have the Lockman Hold and the Cosmos surveys with the VLA. And then we have the IMAGE survey with the EMALIN. And on this end, we have the Cosmos survey, the Gusnell survey with both the VLBA and EVN. And I think I should just explain some of these acronyms. So the VLBA, that's a very long baseline array. It's network of radio telescopes spread across the US with maximum baselines of about 10,000 kilometers. Similarly, EVN is a network of radio telescopes spread across Europe, Asia, and one in South Africa, again with maximum baselines of about 10,000 kilometers. So compared, so the higher, the longer the baseline, the higher the angular resolution provided by instruments. So for example, with the VLA, we have a maximum baseline of about 25 kilometers. So looking at this plot, for example, with the SKA, the best we can do, or the corresponding spatial scales at a ratio of about 1.25 will be about 1 kiloparsec. That's the best that we can do at SKA 1 mid. And then with MeerKAT is about 10 kiloparsec. At this ratio is about 1.25, and similarly with the VLA, so that you see that you are not really able to zoom into the cause of these objects. We are not really able to spatially resolve out these faint radio targets. But then on this end with the VLBI, which gives us an angular resolution of about 5 milliarcsecond, which corresponds to spatial scales of about 100 parsec at these ratios, and therefore you see that you're really able to zoom into these objects, and therefore VLBA provides us with a powerful tool to hunt for this elusive AGN, enabling us to spatially resolve specifically this very faint radio core AGN from star formation. So yeah, touching with this wide field VLBI. So for a very long time, VLBI has been limited by a very small field of view, whereby we have only been able to image the central few arcsecond of our image of our field of view, and then this corresponds to a small sample size, and this for a long time this made VLBI quite unattractive for scientists, because the scientists will like more data. Yeah, so we are trying to change that, and we've come up with several techniques. And the key objective here is that we want to increase the sample size of our VLBI experiments so that at least we can attract more scientists into the field. So one of the techniques is the multiple phase center correlation. And without getting into too much details, so this is your primary beam, or this is the field of view of your VLBI experiment. So what happens if you were to correlate across the entire field of view, you'll end up with hundreds and hundreds of terabytes of data. And what happens is that about 99% of this data is just noise. So because you're only interested in a small region of, you're from the entire field of view only interested in a small region. So what you do is you pre-select points of interest, which you refer to as the phase centers, and then you place your phase centers across your region of interest, and then you simultaneously correlate across your regions of interest or your phase centers instead of correlating across the entire field of view. Because if you are to correlate across the entire field of view, of course, we end up with these large data sets, and I think, we don't have sufficient computational resources to process all the data. So what happens is, in this case, you just correlate your data across the region of interest. So I'll briefly touch on this later. So we have two strategies for this multiple phase center correlation technique. You can select your phase centers based on your region of interest, so you uniformly place your phase centers across your region of interest. Or the second strategy is whereby you pre-select your phase centers from prior non-radio positions. So when you're correlating, you're only correlating across that point in the sky because you know there's a radio target there, possibly from a VLA observation. I'll touch on that later. So what happens in this case is that you end up with lots of small data sets in terms of field of view and size. But what happens is that you only need to perform calibration on a single phase center, and then you transfer your solutions to all the remaining phase centers. So this makes life easier, and in turn increase your sample size. The second technique that we employ in this wide field and the application of wide field VLBI is the multiple source self-calibration technique. So for VLBI, we perform something during our VLB experiment. We perform something we refer to as the phase referencing. So phase referencing is whereby you observe your target and then observe a very bright calibrator within the vicinity. Because remember, like I said, 99% of our targets are very faint, and what will happen, it's difficult to perform not just self-calibration, but also calibration on the target itself. So what happens during observation is you move from your phase calibrator, which is a very bright object within your field of view. And then, so you spend like maybe 5 minutes or 10 minutes on the phase calibrator, and then you move, maybe spend an hour on your target and back and forth throughout the experiment. So you're observing 5 minutes, 1 hour, 5 minutes, 1 hour, so that you can derive your corrections based on the phase calibrator and then transfer your solutions to the target. But then the phase calibrator sometimes is usually maybe about 2 degrees away from our target, and therefore you can see we have these atmospheric and ionospheric effects, which reduces our image coherence. And furthermore, like I mentioned, it's very difficult to perform self-calibration on your target because they're very faint. And so what we do is, within the field of view, we combine multiple response from all the faint targets in your field of view to derive a model that can sufficiently resolve out your source structures. So for example, this is just with standard phase referencing of this target. So you have a signal to noise ratio of about 4:3, and then combining multiple response from multiple targets in your field of view to derive a model that can sufficiently resolve all this source structure. You see that we increase the noise, the signal to noise ratio from 43 to 113 of the same target. So those are the key 2 main techniques that we are currently employing in order to improve the sample size and also the quality of our VLBI dataset. Just highlighting some of the current wide field VLBI surveys, and I really like to highlight this. So we have the Goods North coverage with the EVN. So in the early 2000s, we only detected 3 sources. That is from the Goods North field with the EVN. And then a few years later, about 10 years later, with the slightly improved software correlators, improved computing facilities, we increased the number of sources from 3 sources to 13 sources in the same field with the same instrument. And then a few years later, applying both the multiple phase center correlation technique and the multiple self-source calibration technique, we increased the number of sources all the way from 13 to 31, again, with the same field, with the same instruments. We have other wide field VLBI surveys. For example, we have the Cosmos Field Survey, VLBI Cosmos Field Survey by Herrera Ruiz. We have the VLBI Goods North Survey by Roger Dane. And then we have the Sparks North field. This is whereby we combine both the EVN and EMALIN to carry out a wide field VLBI survey. And this is the first time that this was being done. So the Goose North field is one of the well-studied extragalactic field across all wavelengths. And it's also the only extragalactic field with VLBI coverage by the 2 main VLBI instruments, that is the EVN and the VLBI. And I carried out a performance analysis trying to compare the performance between the 2 surveys, that is the EVN versus the VLBI observation of the same field. So for the VLBI survey, we employed our observing strategy. We used the uniform or contiguous coverage of the Goose North field, whereby we placed 205 phase centers across the region of interest. But for the EVN, these 699 phase centers were pre-selected from a prior observation from the VLA. So for the EVN, that is non-contiguous coverage of the Goose North field. For the VLBA, we detected 24 sources at a sigma of 5.5. And for the EVN, we detected that 1 source is at a sigma of 7. And the difference in the number of sources clearly can be seen because the field of view for the EVN is 15 arc minutes in diameter, but for the VLBA is only 9 arc minutes in diameter. But then again, we detected 6 more sources in VLBA that remained undetected in EVN at sigma about 4.5, and we're able to push down our sensitivity to these levels due to the availability of auxiliary data. So the sources we detected at a sigma of 5.5 were confirmed as true detections using auxiliary data. So remember that very bright object that we saw in the first few slides at 22 millijansky. Like I said, this is a very small fraction of these extragalactic radio sources. We observed the same target with VLBI just to confirm that indeed this is an AGN and not something else. And with VLBI, we resolve this extended radio emission, zoom into the core of this target to reveal this VLBI core. And again, accompanied with things like brightness temperature, we can indeed confirm that that's indeed an AGN. But what is interesting is this very faint source. For this source, if you do not have auxiliary data, it's very difficult to classify this target. And what happens most of the time is that these objects are usually misclassified as star-forming galaxies or star formation. But then with our VLB observations, again, we zoom into the core of this very faint target, which represents a large fraction of our targets. And we're able to confirm that indeed this is a radio AGN based on VLBI detection and also brightness temperature measurements, which I'll get into in a moment. We've also detected merging galaxy system, and I like to highlight this source because this is one of the sources in the Goose-North field, again, well studied across all wavelengths. And what was interesting in the literature, we couldn't seem to agree what this target was. Others classify the target as a starburst, others as a star-forming galaxy, others as an AGN. So the classification was all over, and it was very interesting looking at the target because, so this is the object as seen in the optical. I'm not sure whether this is DAISY or SDSS data. And then we have the same object as seen with with Emalin at slightly high angular resolution. So this is about 1.5 arcsecond, and this is about 0.2 arcsecond. And with Emalin, we detect two radio cores. So we have a very strong radio core here, and then we have a second faint radio peak here, with the second faint radio peak coinciding with our VLBI detection. And based on things like brightness temperature, it has a million, the brightness temperature of this faint core is about 100 million Kelvin, and also very high luminosity. We can confirm that this is indeed an AGN, and therefore what this is implying is that in this system we have both star formation and AGN, so we have a coevolution of both, indicating a merging galaxy system. Again, just stressing the importance of VLBI observations in this merging galaxy system, just to confirm the coevolution of both star formation and AGN accretion activity. We've also made some very interesting astrophysical phenomena discoveries. So, for example, possibility of a dual AGN or a binary supermassive black hole. So for this very interesting target, as seen with the VLA here, we have these points A, B, and C. Again, if you don't have any auxiliary data, you might classify these as three distinct galaxies, and probably might classify them as star formation. So this is an angular resolution of about 1.5 arcsecond, and then we have the same target as seen with Emalin at an angular resolution of about 0.2 arcsecond. So we resolve out these structures at A and C to reveal these age-brightened side lobes. The component at B remains unresolved, and then we come in with our VLBI observations with about an angular resolution of about 5 milliarcsecond, and we partly resolve all this structure at B to reveal two VLBI components. And again, based on brightness temperature measurements, we can confirm that indeed there are two VLBI components. And what is interesting is that it's a very faint component, and you really have to pay attention in how you process your data in order to detect the second component. Again, my message from this slide is that there's a probability that these dual AGN or binary supermassive black holes are not as elusive as we think, just that maybe at the moment we are only limited by the sensitivity of radio instruments. We have other discoveries of binary supermassive black holes from this wide field VLBI surveys, for example, in the Cosmos field by Herrera Ruiz using the VLBA. We have the potential of a binary supermassive black hole again in the Gusnell field using the EVN, and this very interesting triple black hole system again using the EVN. So one of the key properties, measurable properties from VLBI is the brightness temperature. And so when it comes to VLBI, anything detected with a brightness temperature greater than 100,000 Kelvin is definitely an AGN, because at this redshift, that is a redshift of about a ratio of about 1 to 2 is definitely an AGN, because I mean it's very rare to find other objects with this very high brightness temperature at that redshift. So 100,000 kelvins is our cutoff for AGN. And then, so in this plot, I show our 24 targets as seen with VLA, EMALIN, and with the VLBI, so both EVN and VLBA. You can see that if you just based on brightness temperature, for example, measurements of VLA, most of our targets will not qualify as AGN. For EMALIN, which gives us intermediate spatial resolution scales, it's about a few sources will be classified as AGN. But then with VLBI, we did confirm that our targets are AGN. But below this line, it does not mean that this is just star formation only. This is a mixture of both the star formation and AGN, and that's why we require these very high sensitivity observations in order to disentangle or remove the AGN that is in this section. So what does the future look like? Of course, the future is SKA plus VLBI for the VLBI people. We carried out VLBI simulations by adding EVN to MeerKAT or adding MeerKAT to the EVN. And yeah, we did these 24-hour simulations of the system. So this is a simulation of the system for the VLBA only. So this is the UV coverage, and this is the output. This is for the EVN, again, the output, and then this is the EVN plus MeerKAT. And what is interesting, if you look at EVN alone, you see that UV coverage from mid to long baseline is quite poor. But then if you add a little bit of MeerKAT, you see there's a slight improvement in your UV coverage along these long baselines. Yeah, and yeah, just trying to clarify this using this plot here, you have the sensitivity of these simulations and the corresponding UV distance. So looking at, for example, with starting with the VLBA, you see that the VLBA is very powerful. It's very, at medium to long baselines. So using at these short baselines, your data from VLBA is the best. But then remember that the corresponding spatial scales will be different. So it's a matter of, it's a trade-off. Yeah, you can clearly see the angular resolution of the scale size. So you need your very high angular resolution and you need your very high sensitivity. So you need to be somewhere here for your ideal observations in order for you to detect this AGN that is somewhere here. So you see that at longer baselines, your sensitivity for the VLBA completely falls off. And then we have the EVN here, which is the same as EVN plus MeerKAT at this medium to long baseline, short to medium baselines. But then what is interesting, our EVN sensitivity increases on these long baselines as compared to the VLBA. But then when you add MeerKAT to EVN, you see that you massively increase your sensitivity of your VLBA experiment. And again, so you have this very high spatial resolution and high sensitivity, which is ideally what we really want. And just to mention about the EVN, you see that the sensitivity is quite poor along these medium baselines, as nicely shown on this UV coverage plot. The reason for that is because this UV coverage of these long baselines is only provided by a single telescope in South Africa, that is the Hartbeespoort Radio Astronomy Observatory. And then we have all these other antennas in the north, mainly in Europe. So we have nothing in between. So our UV coverage in these medium baselines is quite poor for the EVN. And again, the sensitivity along short baselines is quite good for the EVN. This is because we have a number of very powerful large radio telescopes within Europe, within very short distances from each other. For example, we have the Lovell telescope, which is about 100 meters. We have the Effelsberg telescope. So the sensitivity along these short baselines is quite good for the EVN, but poor along these medium baselines due to lack of radio antennas in between. So there was a proposal to convert a number of telescopes across the African continent for radio astronomy purposes. Some of you might be familiar with the African VLBI network or the EVN, and these are the SKA member partner states in Africa. So for my MSc, I carried out simulations looking at the impact of such an African VLBI network would have on existing global VLBI networks. That is the EVN and the LBA, that is the long baseline array in Australia and New Zealand. So specifically for the EVN, I looked at the UV coverage at a declination of about 20 degrees. So this is the UV coverage. Again, you see these poor UV coverage, nothing in between. And yeah, so you see this poor UV coverage at long baselines and nothing in between. And then I added the avian antennas. So these are the antennas in Zambia, Kenya, Madagascar, Mauritius, and Nigeria. And you can see there's this massive improvement in the UV coverage along medium to long baselines. So to improve the UV coverage, I added even more antennas across the African continent. So I added antennas in Ethiopia, Egypt, Morocco, Senegal, and Nigeria. And you can see we have this almost uniform coverage in the north to south direction, massively improving our sensitivity of this observation. So just showing what these antennas in the African continent could bring on the table for this VLBI experiment. We have this white paper for stating the case for VLBI with Meerkat. We also have an SKA VLBI working group. So if interested, have a look or just reach out. So the key takeaways from my presentation is that with this VLBI, wide field VLBI surveys, we're already covering a parameter space that will only be covered in SKA2 and the NGVLA. And what do I mean? So we have this figure here showing the angular resolution and the corresponding spatial scales at a ratio of about 1.2. So this is for the SKA2 mid and SKA1. But you can see with our VLBA, EVN plus EMAL, we're already covering this parameter space that will only be achieved in SKA2. So we already have these data sets that can be used for various technical verifications and so forth. Again, we have lots of data from our VLBI surveys. So if any students is interested, just kindly reach out. And lastly, I think the most important thing in terms of science is that VLBA will play a very critical role in identifying AGN in these distance fields or SKA sky due to, for example, lack of radio excess measurements, because we don't have enough far infrared radio telescopes. So we don't have far infrared telescopes. Also, the field of view for ALMA is too small. And also our current radio instruments have insufficient resolution to spatially resolve this AGN from star formation. So we definitely need VLBI once SK is fully operational. So leave with that. Thanks for your time. Thanks for listening. I'm happy to take any of your questions.
Oh, thank you very much, Anne. Very nice talk.
Thank
Well
you.
done. Yeah, I will now open the floor for questions. Any questions for Anne? Yeah, I will go for it. Raul?
Okay. Hi, sir. Can you hear me?
Yes.
Yes. So I wanted to know how did they get the brightness temperature to distinguish between AGN and the star formation?
Good question. So we have an equation for this. So you basically use the measured flux density and then this the resolve out. So the size of your radio component and then the redshift as well. So we have an equation for this, but you need the flux density measurement from your observations.
Okay. So
Okay.
do they use a well-known flux density from research prior?
Yeah, so essentially from your radio observation, you measure flux density, right? And then from you have the sizes or the beam sizes at least, and you can use that to calculate the brightness temperature. Actually, I've just done this because I was just finishing a code while listening to the talk, because Kala from Sarao has just gotten approval from China that they will put in what they call, it's an African to the Moon project to take small antennas at low frequencies and put them on the moon and use them to do VLBI. And they asked me which source will be observable. So I wrote, it's not very clean, but I did that quickly. The equation is there. The brightness temperature will be equivalent to 1.22 times 10 to the power 12 multiplied by 1 plus the redshift, if the object has a redshift, multiplied by the flux density you would have measured from your radio observation, divided by the square of the frequency at which you're observing, multiplied by the maximum angular size and the minimum size. But I assume theta there is just the size. I assume is going to be the same. So yeah, that's the equation for brightness temperature, Raul.
Okay, sir. Thank you so much. And my second question is based on the flux and on the flux density plots where you had EVN, VLB, pi, and VLA. This one. So I wanted to know. I got confused when you said that when the highest steps, for example, VLBA, when you have high steps at, let's say, it can't read that one. So the high steps, I just wanted to know, do they represent high sensitivity?
Okay, I get what you mean. This is this is a bit confusing. So high sensitivity here, we mean that your RMS value should be as low as possible, basically. So if I was to draw an arrow, it should be pointing downwards.
Yeah.
Is that clear, Rahul?
Sort of.
It's
So
a
for
root mean square
RMS,
noise. Yeah.
yeah. So this is basically noise. So you want your noise to be as low as possible.
Thank you so much. I thought it was flux density.
Yeah, I know it's supposed to be that way. Yeah, it's normally confusing, but I get what you mean. Yeah. So you need to be as low as possible.
Maybe the unit is what confused him actually.
That
Can the
is just
RMS?
a unit. Yeah, so that's just the unit of measurement for flux density in radio, microjanskis. So this means microjanskis.
Yeah.
So if we can get to nanojanskis, I mean, that would be the best. So
Shouldn't that be microjanskis per beam?
yeah, it should be peak.
Okay.
Yeah.
Thank you, ma'am.
Gotato?
And thank you for the presentation. My question is a general question. So as someone who comes from, like myself, I come from applied mathematics and electronics and physics with electronics, and I'm trying to transition to astrophysics. What advice can you give me?
Good question. Oh my God. Yeah, that caught me off guard. But it depends what your science is. Again, so your background is electronics and mathematics.
Yes.
There will be a lot of data reduction. There's a lot of applying equations, for example, as you've seen with the brightness temperature measurements. Yeah, I mean, yeah, as much as you need to know how to process your data, because you spend most of your time processing the data, I think it's also important that you understand the science behind what you're doing. So you definitely need to understand what is going on behind the scenes. So you definitely do need to spend time, do a lot of literature review and read a lot, but mainly based on what your background is.
Okay, thank
Because
you.
it can get a bit confusing when you start talking about things like interferometry. Interferometry itself is very complicated, and you might, if at all this was a course offered at the university, it will take at least 2 semesters to understand what is going on behind the scenes. So I would say trying to spend a little bit more time reading on radio. You can there's a very nice book by, it's called Introduction to Radio Astronomy or something. I can share that if I find it later, but spend your time trying and read and know what is happening.
Okay, thank you.
You're welcome.
I see.
Yeah. Any other questions from the floor? Sorry, Anne, I just showed the Peter Wilkinson book.
Yeah, that one exactly. Yeah, radio astronomy. Yeah. So take your time to read the book. You'll find it very useful. It was very useful for me when I was doing my PhD.
And have you considered remaking the simulation? I know you're looking forward to taking a break in 1 month, but it would be nice to have the realistic simulation of what the AVN contribution would be. Now we have confirmation that there is an antenna coming to Botswana and there is another one coming to Namibia. The Moroccans are making moves to get another dish which would be very, very useful as an intermediate baseline to Europe.
Yeah.
So would you consider remaking the simulation again, the CASASIM to?
Yeah, I wouldn't mind. I mean, it can't be that complicated. It's just producing your UV coverage plot from a shed.
Yeah.
Yeah.
Cool. Any other question? I'm keen to see the source where you said there is AGN and star formation. Is that a merging galaxy?
Yeah, it's a merging galaxy system.
Okay, so one of them is dominantly star formation and the other one is AGN.
Yeah.
Okay.
Yeah, and we confirmed this based on the brightness temperature measurements. It's 1,000,000 kelvins.
For which one? For the AGN one?
Yeah, for the one highlighted in red.
And for the other one?
I mean, we didn't detect in VLBA, the second one, which is expected if it's star formation, unless it's a very, very, very faint AGN.
Okay. Oh,
Yeah.
nice. That's interesting. How do you know these two are interacting and it's not just foreground and background?
Yeah, very good question. But again, you can see from radio. Yeah, I cannot tell. I don't know much about the foreground and all that, but you can see that it's a single system from your Marlin observations. They haven't done much probe into this, but yeah, my conclusion is that it was a merging galaxy system because we have these two radio peaks, one in Marlin, which remains undetected in VLBI, and the second one, which is very faint in Marlin, but detected in VLBI.
Yeah, but if you do much higher resolution, you can separate those two cores, right? They will be independent if your baseline becomes longer. So I'm saying, do we have, on the two peaks of the two galaxies, do we have independent redshift measurement for the two?
Unfortunately, we don't.
Okay.
Yeah,
so it's redshift, just one redshift and use for both, and assume that they are both in the same distance. Okay.
Yeah.
Oh, cool. But it looks interesting.
Yeah.
It looks like antennae galaxy to me. So, yeah. Oh, nice. Any other questions for Anne? Okay, maybe we'll thank Annie. Oh, sorry, Stabile.
Okay, thank you for that very informative talk, Anne. It was very brilliant. And yeah, all the best with the next phase of your career, or the break, so to speak. So this is more of a fun question. If you had $1 billion US dollars, how would you design a VLBI instrument to optimize your research goals and interest?
How does design? I'll just add more antennas in Africa.
Okay. All right. Fair enough. But yeah, we need higher UV coverage on the African continent. Okay.
Because I believe if we add more antennas in Africa, then we can improve our sensitivity to nano Janskis levels, and then that means we can detect as much AGN as possible.
Okay. Yeah, that makes sense. Thanks.
Yeah, also you need the intermediate baselines to start seeing intermediate structures in the AGN, I guess.
Yeah.
Right? Not just the sensitivity.
Yeah, definitely. Yeah, definitely. And that's why we try and combine EVN plus Marlin.
Okay.
Because with the EVN, it gives us very high spatial resolution, but then when you bring in Marlin, you start to see this merging. Maybe I didn't show this. Yeah, you start to see this merging to this sub-kiloparsec or parsec scale jet-like structures. Yeah.
Cool. Any other questions for Anne? Francia? Francia, we cannot hear you. Hello, Francia? Oopsie.
Oh, sorry about that.
Okay.
My question is about the dual AGN. So is it two AGN coexisting, or two AGN who will merge later? And from the picture, how can we say that it is a dual AGN because it's really faint?
Yeah, good question. Thank you. So definitely it's an agent based on brightness temperature measurement. Like I said, our cutoff for brightness temperature for VLP experiment is 100,000 Kelvin. And anything at this redshift with that brightness temperature levels is definitely an AGN. What the future will happen, I really don't know. It was difficult to tell because we do not have the redshift values, so we couldn't really conclude whether this is a dual AGN or a binary supermassive black hole, and it's potentially either a dual AGN or binary supermassive black hole, and will require sort of more follow-up to confirm it indeed this is true. So it's a potential candidate in the dual AGN or binary supermassive black hole.
Yeah, I see in that image when you taper your UV to 28 by 22 milliarcseconds, you lose the very compact object, right?
Yeah.
Completely. Oh, wow. Okay. Awesome.
Yep. So this is when you this is only made possible by combining EVN with eMarlin. Allows you to taper. Yep.
Yeah. Because eMarlin gives you the few tens and few 100 kilometer baseline. Yeah.
Yeah.
Cool. No, nice. Any other question for Anne? Good. We're just on the hour. Thank you very much again, Anne.
Thanks for having me.
And enjoy your break. Hopefully we'll see you again soon.
Thank you. Thank you very much.
Thank you.
Have a good day. Thanks.
All right.
Enjoy
the rest of the day. All right. Bye-bye.
Thank you. Bye-bye.
Thank you.
Okay. Bye, everyone.